All right, Huskies, we are going to talk about solving inequalities as opposed to solving equations, which is what we've done so far in this unit. Now we're going to solve things that are not equal. Our objective, I can solve and graph linear inequalities. Often it's useful to show the answer to an inequality on a graph. So that's why we're going to graph it. I took a different tack to this in class. We did kind of a little discovery thing. I'm going to teach this a different way on this video. I'm just going to show you the difference between an equality and an inequality. So if you were slightly confused in class, maybe this will help sort things out. I don't know. Let's solve the equality that we have here on the left. An equality is just another name for an equation. See that? We have an equal sign. It's an equation. This is a simple equation that you have been solving so far in this unit. Should be kind of second nature by now. Let's add 1 to both sides. And so we would get that 6x equals 30. And when we divide both sides by 6, we get that x equals 5. We have solved our equation. We know that there is one number that will work when you plug it in for x into this equation. 6 times 5 is 30, and 30 minus 1 is 29. This equality has one solution, just one number. Now, look at the inequality. All the numbers are the same. The variables are the same, 6x minus 1. But instead of being equal to 29, it's greater than 29. So if we were to solve this inequality, we could sort of do the exact same steps. We would get that 6x is now greater than 30, and divide both sides by 6. We would get that x is greater than 5. Now the difference is in the solution, because we no longer have just one solution, not just one number that works in here. This says that any number greater than 5 is a solution to this inequality. Well, how many numbers are greater than 5? 6, 7, 13, 827, 5.01. There are an infinite number of solutions to this inequality, because I could choose any number bigger than 5 and it would work in this inequality. For example, let's just pick 10. Let's say that x is 10. Is 10 greater than 5? Yeah. So it's a solution. 6 times 10 is 60, and 60 minus 1 is 59. Is 59 greater than 29? Yeah, so that works. It's a solution. And I could show all of my solutions on a number line here. I could say, oh, well, if this is 5, this is 6, and this is 7, etc., then my solution would be all these numbers that are bigger than 5, like 6 and 7 and 8 and 9, but 6.5 and 7.3 and 5.01. So we're going to talk more about graphing later, but you can see that by just marking the dots for all the numbers that are greater than 5, I could represent all the solutions to that inequality. Okay, let's do another one. This time we're going to solve the equation negative 3x plus 4 equals 19. And the inequality that matches is negative 3x plus 4 is less than or equal to 19. Now in class we kind of discovered this rule, but I'm just going to straight up tell you that there is one extra rule when solving inequalities that does not apply to regular equations. If I subtracted 4 from both sides of this equation, then I would need to divide both sides by negative 3, so x equals negative 5. It's pretty straightforward. However, when I solve an inequality and the last step involves multiplying or dividing by a negative, there's one extra rule you have to know. This step right here, when I'm dividing by a negative, I have to reverse the inequality sign so that x is going to be greater than or equal to negative 5. Notice how it used to be less than, now it's greater than. The sign reverses anytime you multiply or divide both sides by a negative number on inequalities. And here I am dividing by negative 3, and so I had to reverse the sign. That's the extra rule. So here's your strategy. When you have to solve inequalities, you're going to just pretend it's like an equation. Follow all the same rules, you know, all those same steps that we talked about when solving multi-step equations, except if you have to multiply or divide both sides of that inequality by a negative number, then you have to reverse the inequality sign. And again, in class we talked about y. I'm not talking about y right now. I'm just trying to help you understand that that's the one extra rule. Okay, we're going to practice a bit here. So if we are told, where are we? I think this is 5A. There we go, 5A. We're just supposed to graph the answer here. I just want you to show me what it looks like. Let's graph all the numbers that are less than 7. Well, there's a couple different ways you can do this. If I'm going to talk about all the numbers less than 7, let me just make my pen fat here. Is 0 less than 7? Yeah. Is 1? 2, 3, 4, 5 is less than 7. 6 is less than 7. How about is negative 5? All these work. All these integers work. Are there other numbers here that are less than 7? Is 1/2 less than 7? Sure. How about 1.9? Yeah? Okay, so you can kind of see that I could keep picking numbers. They don't have to be integers. They could be fractions and decimals that are less than 7. And I'm going to just, by plotting a dot for each one of them, I'm going to fill up this entire number line. In fact, I'm going to color in the arrow also to show that it's just going to keep going that direction. All those numbers are less than 7. But what happens when we get close to 7? Is 6 less than 7? Yes, but so is 6.5 and 6.6 and 6.7. We can get all the way right up to 7, but it cannot equal 7. It has to be less than 7. And so to show that it cannot actually equal 7, we put a force field around the 7. Oh, can't touch this. You can come right up to 7, but that bubble, that force field, is protecting you from touching this 7. And so when you have to graph these, we're going to just color in the whole number line and go right up to the circle, but not equal to 7. Okay, I'm going to do C next instead of B. We'll come back to B. C says we're going to graph all the numbers less than or equal to 5. Okay, we're going to color in the number line all the numbers that are less than or equal to 5. All these numbers down here, but this one's a little different. This one could actually equal 5 because 5 is less than or equal to 5. So this time, when I put the circle on the 5, I'm going to color it in to show, yes, it could actually equal 5. And everything that's less than 5. That's what it means to be less than or equal to 5. Some people like to do their coloring above the number line, so they would like color in the dot like here and just draw an arrow above the number line. That's totally fine. If you want to do it that way, that's great. I didn't do it that way when I was learning, so I probably will never do it that way, but if you want to, I understand what it means. You can do it. Let's go back to B. I put this on here because I often hear students say to each other, "Joe, dude, just shade it in the direction of the arrow," like saying that this inequality sign is an arrow, and if it's pointing to the left, then you have to shade left. Well, what's wrong with that? That worked on A and B. Well, the problem is that only works when your variable's on the left, and most students don't realize that that little shortcut has limitations. So, for example, on B, you could not just shade this to the right because the arrow is pointing to the right, because let's use some common sense, some logic. Let's talk about what this inequality means. It says that -2 is greater than a number. Pick a number that is -2 is greater than that number. Let's see, -2 is bigger than -100. -2 is bigger than -3. Remember, the closer you get to 0, you know, that's going to the right, that's getting bigger. So -2 is greater than -5. Well, all these numbers that I'm listing in this position, -100, -3, -5, those are solutions to this inequality. And so I would actually color let's see, here's negative 2, but negative 2 is bigger than everything on this side. What do you know? I'm shading to the left, not to the right, because dude's not an arrow. I'm shading to the left because if you were to read this inequality from right to left, it would actually say x is less than negative 2. And all these numbers that I've chosen here, negative 100, negative 3, negative 5, those are solutions that are less than negative 2. So please don't just mindlessly shade in the direction of the arrow. It won't work. It'll lead you astray. Use some common sense and pick a number from your shading to plug into the inequality to test. For example, on A, I shaded in 0 right here. See that? 0. If I put that into this inequality, is 0 less than 7? Yeah. Okay, it works. I did it right. I shaded it on the correct side. Okay, so we are on the back. Yeah, number 6. Solve it and graph it. So, like I was saying before, you're just going to solve this using your basic rules for solving a multi-step equation. But at the very end, if you have to multiply or divide by a negative, then your sign is going to reverse. Okay, so I'm going to subtract 2x from each side. I'm going to bring all my variables to the left-hand side. And the 4 is still there. This is now negative 5x. Hey, there's a 5. And it's going to be less than just negative 1 is left over there. Okay, I can combine these like terms so that it's going to say negative 5x plus 9 is less than negative 1. What if you said 9 minus 5x? Is that okay? Sure, totally fine. And I need to now move my 9 to the other side so I can get just the variable by itself. So I'm going to have that negative 5x is less than negative 10. So far I've just done all the same rules, solving a regular old equation. Nothing has changed. You can even draw that line if you like. Well, I didn't really make mine straight, but you know, you can draw the line through the less than sign if you want to treat it like your equals. The party wall, Mr. Woolley calls it. Now we're at the very last step here, and we're going to divide both sides by negative 5. There should be an alarm going off in your head. It's the dividing by a negative alarm that goes off when you are dividing by a negative on an inequality. And that alarm is reminding you that you actually need to reverse the inequality sign at the very last step, because that's what you do. Negative 5 divided by negative 5 was 1. Negative 10 divided by negative 5 was 2. But we had to reverse that. Now instead of saying x is less than, we're saying x is greater than 2. So how do we graph this thing? Well, you're going to go to 2. It does not have an equal sign. This cannot equal 2. It can't equal 2. So you got to put the force field around it. Can't touch this. Can't touch the 2. But it could be everything bigger than 2. X is greater than 2, so I'm going to shade in everything bigger than 2. And I shade in the arrow to show that it keeps going forever. That's my beautiful high quality shading done with my finger on the iPad. Da, 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 da. If you don't like coloring and you just wanted to do this above the picture, that works as well. Okay, let's practice some more. Here's number 7. If you just imagine this to be an equal sign right here, then da-da-da, we have our landmark multi-step equation with a variable on each side and a constant on each side. I know you know how to do this. I'm gonna do it in a different color. I'm going to add 3x to both sides. I'm just going to bring everything to the right this time. Remember, I've told you before, it doesn't really matter if you bring everything to the right or to the left. It's your choice. And yeah, we could treat this as our line right there. So these added up to be 0. Yay for 0. And now I'm going to subtract 13 from each side. Have I multiplied or divided by a negative? No, not yet. And I'm not going to multiply or divide by a negative because I did this. And by moving everything to the right, I just got positives. I do have to divide by 8, and so I get that 1/8 is greater than or equal to x. Okay, we don't usually like to have it with the variable on the right-hand side. It makes it a little bit weird for our brains to think about. So if you switch that around and read it from left to right, it would say x is less than or equal to 1/8. Now, I'm just going to keep that there, and I'm going to go back and I'm going to erase all this work that I just did, and I'm going to do it again from the beginning, but I'm going to move all the variables to the left instead. Just to show you that, oops, it does not really matter. And it'll give you a little bit more evidence for this whole switch the sign thing. Okay, so I'm going to subtract 5x this time so I can bring all my variables to the left. I have 14 minus 8x is greater than or equal to 13. I will subtract 14 from both sides. Remember the sign in front, there's that invisible plus sign there that tells you you need to subtract it. This negative sign is staying with the negative 8. That's what makes the 8 negative. So here I get 0, and I just have negative 8x is greater than or equal to negative 1. Oh, got to divide by negative 8. Oh, the alarm went off. Okay, so that means I need to reverse my inequality, and I get x is less than or equal to positive 1/8. Hey, that's the answer we got the first time we did this. And that shows you another reason why you have to reverse that inequality. If I had just left it as like the less than or equal to that it was, the greater than or equal to that it was at the beginning without reversing it, I would have got it wrong. Because that negative just makes it, you can avoid the negative thing and the extra rule by always avoiding having that negative, like I did when I added the 3x to both sides at the beginning. But then I had to read it from right to left instead. So there's always going to be one extra step. Okay, I hope that makes sense. To graph this, it's pretty simple. You don't really care where the fraction is. It's going to be less than or equal to 1/8. You're just going to tell me, oh, that's 1/8, somewhere in between 0 and 1. And x is going to be everything less than or equal to that. So I have a solid dot because it might actually equal 1/8. Don't need a force field. It can come right up and touch the 1/8. It can equal, less than or equal to 1/8. Okay. Okay, now this next one, it's not really much harder, but there's a little pitfall here with the distributive property that you need to watch out for. You see the parentheses, you know you have to distribute, but don't forget to bring this negative with the 3, this negative right here. So the 4 cannot be combined with that negative 3. You can't add or subtract those because the 3 is being multiplied by what's in the parentheses. So just recopy the 4 and we'll deal with it later. And then you're going to get negative 3 times x is negative 3x, and negative 3 times negative 4 is positive 12. And everything else I'm just going to recopy. Now I can deal with that 4. I'm going to combine it with the 12 so that I get 16 minus 3x is less than or equal to 2x plus 1. Okay, do you want to bring everything to the right or the left? Let's bring it to the left just so we can practice our rule. And by doing that, we're going to have 16 minus 5x is less than or equal to 1. Well, we got to get rid of the 16 now. Remember, the invisible positive in front of it is why we're subtracting, because it was actually being added. So I have negative 5x is less than or equal to negative 15. Okay, divide both sides by negative 5. That alarm should be going off. Dividing both sides of an inequality by a negative tells you reverse the inequality. So now it's greater than or equal to positive 3. Here's positive 3. Could it equal 3? Sure. Let's put a big fat dot on there to say that it could equal 3. We're not trying to protect the 3 from being touched. We're trying to say it could equal 3. So it can equal 3 and anything bigger than that. Color in the arrow to show it keeps going forever in that direction. Okay, just a little review. If it's less than or greater than, it's an open circle. If it's less than or equal to, greater than or equal to, it's a solid circle because the line there tells you it might be equal. So you're going to color it in to show that it could actually equal. By the way, while I'm thinking about it, less than, how do I know which one of those two symbols is less than? Well, less than looks like a squished L. See the capital L here? If I were to squish that a little bit, then I know that's less than. So looking at it from left to right, if it looks like an L that's been bent a little bit, that's the less than sign. Okay, well, we're going to talk about compound inequalities now for a second. So a compound inequality is when you have two inequalities, and we're looking down at number 9. So in class I talked about my dog and his weight, and so we're trying to talk about what the weight of a dog might be that is healthy. The healthy weight of a dog, of my dog, would be between 60 to 75 pounds. That would be the healthy weight of my dog. Well, in math, we are going to write that as a compound inequality. We're going to say the healthy weight, x, it's going to be between 60 and 75 pounds. Think about what this is telling you. At the same time, the weight has to be bigger than 60 and less than 75. That's what would be healthy. Could it equal 60? Yeah, it probably could. Could it equal 75? Yeah, that's probably still okay. But anything outside of that range is not going to be healthy. So a compound inequality is when we are using more than one inequality sign. That's one way to write it. Another form of compound inequality is if I were to say, what's an unhealthy weight for my dog? Well, an unhealthy weight would be if my dog weighed less than 60 pounds, or like that'd be too skinny. Or if my dog weighed more than 75 pounds, that would be too fat. Either of those is unhealthy. So why did I have to use the word or here, and I didn't use the word up in this one? Well, inside this compound inequality, it's kind of a shortcut for and. So I'm actually saying in this case that I can be, my dog, could be greater than or equal to 60 and less than or equal to 75 at the same time, and that would be healthy. And so, and means that they both have to be true at the same time. This dog needs to be greater than or equal to 60 pounds and less than or equal to 75 pounds at the same time. Because if it was just greater than 60, well, if my dog weighed 100 pounds, for my dog, that would not be healthy. So it has to be, both have to be true at the same time. That's what the and is. Both of them have to be true at the same time. But or, it could be this or that. So unhealthy would be less than 60 or greater than 75. So they're different. These two tiny little words are called conjunctions. And they're called conjunctions in English as well as math. Conjunctions. In fact, there's a Schoolhouse Rock song called Conjunction Junction. What's your function? And button or, they'll get you pretty far. I don't know if you know that song, but conjunctions, these two little words, we often skip over them because, what? Or, 2 letters. What a big deal. But it can change the entire problem. So you have to pay attention to those two tiny little words, and they will tell you if it's going to be something that's both true at the same time, like and, or if it's just this or that, one or the other. Okay, let's practice. Here's some compound inequalities. I've written them both out with words, but you can combine when it says and, you can write it in a little bit easier looking compound inequality. So, compound inequality, x is less than -3 or x is greater than 10. What I want to do here is actually just graph that. What would that look like on a graph? Well, it's two things are going on here. Sorry about that. I should have had a graph ready. let's say that this is -3, -2, -1, here's 0, there's 10. Two things are going on. This compound inequality is saying that my solutions, the answers that I want, are either less than -3 or greater than 10. This is like the unhealthy weight of the dog. You know what I mean? Like, it could be bigger than 10 or could be less than -3. So the graph of it is going to be like, well, it could be less than -3. Any number less than -3 would work, or so would any number greater than 10. That would also be a solution. That would work. Is 0 a solution to this compound inequality? No. It's not less than -3. It's not greater than 10 either. So nothing in this empty spot right here in the middle is a solution. It's only the stuff on the outside, or usually goes out. Or usually goes out, like that. So all the ones that we're going to do, or will go out. Okay, so then if we're going to graph this other compound inequality, the thing with the and has to both be true at the same time. So, yes, super excellent, evenly spaced marks there. So here's my -3. 0, 2, 4, 6, 8, 10. Okay, so here's 10. So this one has to be greater than -3 and less than 10 at the same time. If I were just going to graph everything that was greater than -3, it would just go that direction. And if I was going to just graph everything that was less than 10, it would go that direction. But if it's the word and, if that's the conjunction we're using here, then it's just where those overlap, where they're both true at the same time. So this compound inequality on the graph would actually just be everything between -3 and 10. And I love to use the word between when I talk about an and compound inequality, because to me, it would make a lot more sense if I just wrote this as -3 is less than x and x is less than 10 at the same time. Hey, look at that compound inequality. Isn't x literally between -3 and 10? It is. It's sandwiched inside there. X is greater than -3, but at the same time, it's less than 10. And so if you line up your numbers so that the smallest one is on the left, just like the number line. It's like this little number line here. Let me do a pointer. This number line picture is just another way of looking at this compound inequality. Can you see the number line there? Here's -3, here's 10, and x is all the stuff in between. All the stuff in between. Okay. Let's say that I don't know, here's an example from the real world. Let's say that I tell you, you're my kid, and I'm like, oh, you can go spend $15 to $20 on a gift for your brother, or something like that. $15 to $20 on a gift. What does that mean? Well, you know that means that you could spend $15 or $16 or $17 or $18 or $19 or $20. You could spend $17.50. You could spend $18.03. You could spend anything between $15 and $20 on a gift. Could you spend 15? Yeah. Could you spend 20? Sure. So what I'm saying here is that the gift, let's use G for gift, or C for the cost of the gift. The cost of the gift is going to be between $15 and $20. So this is stuff that we talk about all the time in English, in real life. And if we were going to graph that, it would look kind of like these numbers that I just wrote out here. Like on our number line, we'd have a 15, we'd have a 20, and we could spend anything in between there. It has to be greater than 15 or equal to 15, and less than or equal to 20 at the same time. Because if you spent $0 on the gift, that would not be acceptable. If you spent $50 on the gift, that would not be acceptable. Anything between $15 and $20. Another example is like baking cookies. You could bake 16 to 20 minutes. Well, what does that mean? That means you could bake it for 16 minutes or 17 or 18 or 19 or 20. Just remember, the smallest number always needs to go on the left. Let's talk about an example for or. My husband works for a technology company, and they have a server room full of all these stacks of computers. And they have to monitor the temperature very carefully in these server rooms, because if it gets too cold, the computers will be ruined. And if it gets too hot, the computers will be ruined. So we can't let them overheat. We can't let them freeze up. And it gets really hot with all the computers running anyway. So they have some alarms. They have temperature sensors, and they have some alarms set. And so the alarm is going to go off if the temperature drops below, I don't know what it is actually, 60 degrees, or if the temperature is above 75 degrees. Then an alarm was going to go off. So either one of those temperatures will set the alarm off. What would it look like? What on the number line will it look like for when the alarm is going off? Well, there's the 60 and there's the 75. The alarm will go off if it's less than 60 degrees or if it's greater than 75 degrees. They don't have to be both true at the same time. How could the temperature be both less than 60 and greater than 75? It can't. They don't have to both be true at the same time. Like I said on the gift, they do have to both be true. It has to be bigger than 15. It has to be less than 20. It has to be in between there. But the temperature can't be both cold and hot at the same time. But either one of those, this or that, will set off the alarm. Okay? All right. Number 10. We're going to go opposite now. I've given you the graph, and you get to write the inequality. So write the inequality represented by this graph. Well, -4 is shaded, so I'm going to follow my number line, and I'm going to write down from the smallest to the biggest number, left to right. -4 is on the left, and 2 is on the right, and I'm going to let x represent everything in between, because the number line is actually the x-axis. It's like, you have x, y, like graphing linearity and stuff. Well, we are just ignoring that y-axis, so a number line is always just thought of as the x-axis. So x. So -4 to 2, but now we have to decide about our inequalities. So we really have 4 choices. Here are the 4 choices. Now, when you set up your number line, and your number line should always have the smallest numbers on the left. Always. It should always be getting larger as you go to the right. If you've set up your number line properly, then you should never ever need to use these signs for a compound inequality that's shaded in between. It's always going to be a less than, because just of the nature of, it's getting bigger as you go to the right. So -4 is going to be less than or equal to x, and x at the same time is going to be less than 2. How did I know that this was a less than or equal to? It's because the dot was solid. How did I know this one was not a less than or equal to? It's because the dot was hollow, the force field. Okay, let's look at another one, number 11. Now this one has the word or. So I want you to think about, what does that mean in words? It means that x is less than -2, or x is bigger than or equal to 5. This one or that one could be true, and you're not really sure which one is true, so you just graph both of them. But that's what the words mean. X is less than -2, or x is greater than or equal to 5. That's all I want you to write down, and I'm not going to take the time to write it down, but you are, because it's your classwork. Number 12, what's the inequality represented by this graph? Well, kind of like what we did before, I'm going to see, there's a -6 and 7, it looks like. But it's not shaded in between this time, so I'm not going to write my x in between like we did before, because this is not an and. They're not both true at the same time. This is an or. It's going out. So that means that x is I'm going to have 2 separate inequalities with the word or in between. Or, very important conjunction. So, how do I know which sign to use? Well, let's see. I've colored in all these numbers that are smaller than -6. So that means that x must be less than -6. But wait, my dot is solid, so it must be less than or equal to -6. Okay, what's going on over here? I've colored in 10. 10 is bigger than 7. I've colored in all these numbers that are bigger than 7. So x must be bigger than 7. Greater than. But wait, my dot is solid. So that means that it must be or equal to, because it might equal 7, might equal -6. Either one of those is true. Okay, let's graph these two. The numbers are the same, -1 and 4. Numbers are the same on each one. So I'm going to talk about -1 and I'm going to talk about 4. I'm going to talk about -1 and I'm going to talk about 4. So far they're exactly the same. Now I notice that there's an equal to sign on the -1, so it's going to actually, it could equal -1. I'm going to color that in because it might equal. It's less than or equal to. All right, so that's that. Now on number 13, just looking at the compound inequality, x is literally between -1 and 4. X is in an inequality sandwich between -1 and 4. Well, your graph should reflect that. It is sandwiched, it's smushed in between there. X is all the numbers, any of the numbers between -1 and 4 will be a solution to this inequality. Is 0 a solution? Yeah. Is 3 a solution? Uh-huh. Ooh, pi. Pi is a solution. Pi lives like right here. Pi is a solution. It's between -1 and 4. E. You guys don't know anything about E yet? It's pi's buddy, 2.818 ... It's also an irrational number. You'll learn about that in maybe 11th grade. It lives there too. So we have pi, E, 0, 1, fractions, decimals, all of them are solutions to this compound inequality. What's different on number 14 though? 14 says x is less than or equal to -1. Well, that's going out this way. All these numbers over here are smaller than -1, less than, and, I should say or. Because the solutions might be over here, or they might be bigger than 4. We don't know where the solutions are. Could be -8, could be 32. I don't know. As long as it's less than -1 or greater than 4, it will be a solution. Is 0 a solution to this one? Nope. 0 is not less than or equal to -1. It's also not greater than 4, so 0 is not a solution. Okay, so I hope that really helps you with these compound inequalities. I'm only going to do one homework problem. I know. I feel like I've talked a lot already on the classwork, so only one homework problem. And it's just to remind you of the dangers of distributing. Distribute that negative. -2 times -2 is -4. -2 times -2x is positive 4x. Then we have to distribute -4. So I'm going to get a -4x minus 20. And that is all less than or equal to -24. Right? We're doing all the rules of our equations. We're not even paying attention to the fact that that's not an equal sign until the end, when we will have to analyze it and hopefully not divide or multiply by a negative. Well, what are some like terms that we could combine here? Okay, I could, 4x plus -4x, that's just 0. Yay, for 0. Well, then I have here -4 minus 20 is less than or equal to -24. Where are all my x's? What's going on? That's -24, and that's -24. What? Okay, this happens sometimes. Is -24 less than or equal to -24? Yeah, it is. It's equal to, and that is allowed because there's this bar underneath here. So -24 does equal -24. So remember when we were solving the equations, if we came up with something at the end that was always true and there were no x's left anywhere in the equation, No variables, they're gone. What did we say that was? We said that was all real numbers. That's still what it is. I could plug in any number I want for x, and negative 24 is still equal negative 24. So what you get to do here is color in the whole stinking number line. It's every number you can think of. Every one. Color in the arrows. Show that it keeps going forever and ever and ever and ever in both directions. Now, what would happen if you came up with something, let's just say, just in case you run into something like this on your homework. You're solving along, you followed all the rules, and you come up with something like negative 1 is less than or equal to negative 24. Hey man, that's not true. That's false all the time. So that would be no solution. And what would a number line look like that's no solution? I want you to think about that. That's just an example for something you might run into. Good luck on the rest of your homework, and if you still have questions about inequalities, please come see me for some help.